lower Mach numbers. And what enables this is the observation that the non-dimensional parameters will be practically independent of, or can be considered to be independent of, Mach number at higher Mach numbers, because when we have because we can express the governing equations in a non-dimensionalized form independent of Mach number, and their boundary conditions, the relevant boundary conditions are also can also be expressed as independent of Mach number at high Mach numbers. So based on these two observations, we conclude that the flow field and the static pressure distribution can be considered to be independent of Mach number. So that's basically the Mach number independence concept. One second, I guess I forgot to start recording. I guess it's done already. So that's the concept of Mach number independence, and based on or as a confirmation of this, some basic geometries experiments have been sort of confirmative to the conclusion. I have shown this. I just want to highlight one particular point with respect to these two curves. The top one is for the pressure distribution, CP values over a sphere, and the second graph, the lower one, is for a cone cylinder, something yeah, a cone cylinder kind of configuration where you have a leading edge cone followed by a cylinder body. So as we have seen in the previous class, we observe that after a higher once it crosses a particular Mach number, or particularly in the hypersonic range, the CD value, not CP, CD value, the drag coefficient remains almost independent of Mach number. And this is the conclusion we drew based on the observation of the non-dimensionalized boundary conditions and the forms of equation. Another additional point to be highlighted here is that the lower curve is for cone cylinder and upper curve is for sphere. Now I request your feedback on in which case you see the graphs being independent of Mach number at an earlier Mach number. I repeat the question: which of the two CD distributions tend to become Mach number independent earlier?
The sphere, sir.
The sphere one, yeah, the top one. That's because we can see from the graph that, say, maybe somewhere here you can consider it to be, maybe somewhere here you can consider it to be practically being independent of Mach number, or maybe slightly upstream. So if you're if you're looking at a more stricter, this one may be somewhere here close to 4 or so, whereas the second one goes close to 5 or slightly above that. Okay, so here, even before it becomes enters the conventional here Mach number hypersonic range, or maybe just around that point, it becomes or it starts becoming independent of. So what this tells us is that for blunt bodies, the Mach number independence is achieved earlier, relatively earlier than sharp edged or bodies with an attached shock. And this is because of the sine squared m squared sine squared beta that we see in the relations. If I have to show that, yeah, this m squared sine squared beta, which keeps showing up in the all the relations that we have here also, p2 by p infinity m squared sine squared beta. The sine squared beta, when beta is higher, then you will have a higher value for sine squared beta x. So that sine squared beta variation, that is the wave angle variation, has an influence on this parameter, and that, so when sine squared beta is relatively high, m squared sine squared beta tends to be very high. So I mean, when tends to be high, in fact, sine beta we know is going to be certainly less than 1, sine squared beta also. but then higher that value, that product is going to be higher. So which means that the term that we are trying to neglect when Mach number is infinity, that becomes higher when beta is, or the wave angle is higher. So basically that's the reason why blunt bodies tend to be Mach number independent at a lower Mach number. Again, so with that, we move on to, we conclude the Mach number independence discussions, and we move on to the topic of similarity parameters and solutions, or the pressure estimations based on similarity parameters in supersonic. I'll just open that. Similarity. Before we go to similarity, I'll just explain the title that we have given here: hypersonic small perturbation theory. Small perturbation. I'll explain that earlier. Probably you would have, yeah, most probably you would have come across that in aerodynamics. Uh, Let me confirm that. Have you studied about small perturbations in aerodynamics? Small perturbation theory or small perturbation analysis in aerodynamics?
Yes, sir. We
Yeah.
use that to derive things.
Very good. So that is okay. So you have a feel for what small perturbation is. I'll just explain or rather revisit that concept so that we can adapt it more conveniently to compressible, supersonic, as well as hypersonic flows gradually. So the approach in hypersonic flow, to make use of small perturbation theory, is to have similarity parameters. I'll explain that also, that you would have heard of in fluid mechanics and aerodynamics, similarity parameters. We'll revise that anyway. To find out similarity parameters which can be made use of to get again a fairly good estimate of the pressure distribution on bodies. So we'll start off with the concept of small perturbations, the general approach, the approach you would have followed in aerodynamics also, while considering flows past uh, airfoils, etc. The perturbation, that is a small disturbance that is caused by the presence of a body in an external aerodynamic field. So small free stream disturbances as a result of an obstruction. So how does that obstruction impact the flow field? And when such obstructions are relatively less, we consider it as a small perturbation. As We consider those as small perturbations of the flow field. Now, small is a qualitative word, obviously, but then in most of the high speed aerodynamics applications, the velocity field, we do not disturb it a lot, right? We will have a streamlined shape, we will have airfoils, and particularly in hypersonic flows, you will quite often you will have thin bodies, or more accurately, slender bodies. So when you have slender bodies, the disturbance can be considered to be less or small, and that's what we mean by small perturbation. Now, what are we perturbing? We are perturbing, or rather, what are we disturbing? We are disturbing the mainstream properties. So, in the absence of an obstruction, the flow continues with the free stream bodies. I'm sorry, free stream properties like U infinity, M infinity, etc. I'm sorry, I have a bad cold that keeps troubling. Anyway, so what we are saying is that or what we are considering is disturbances or perturbations caused to the mainstream flow properties like U infinity, M infinity, T infinity, P infinity, etc. They are all free stream properties. Now, as I was just saying, in the absence of the body, the flow would have continued with the mainstream properties, U infinity, etc. But then, by the introduction of the body, you are going to have some variation in the external flow field, right? Now, which means that you are going, which in other words means that you are introducing disturbance to the mainstream properties. As a result of this, the flow field gets modified with a new set of properties for the velocity components. Velocity components means the x component of velocity u, the y component of velocity y, and maybe if I am using a third dimension, the z component, which we can call as w. So u, v, and w, the three velocity components in x, y, and z direction. Okay, so now since we are considering the initial flow to be aligned with the x direction, I hope that is clear. That is, if I have a body like this, and I have the flow, the approaching flow coming like this. All that I am saying is that M infinity, V infinity, etc. All that I am saying is that the main flow or the undisturbed flow is along the x-axis. Okay, which means that the to begin with, the u velocity can be considered as u infinity, or the x component of velocity can be considered to be u infinity, not u infinity. And at the same time, the to begin with, the y component of velocity is 0 because the flow is aligned along the x-axis. So v infinity is 0. And similarly, the z component we are neglecting. So there is no flow in the z direction, so you don't have velocity in that direction either. So to begin with, or upstream of the body, the flow is aligned in the mainstream direction where you have u as u infinity. Okay, now the body disturbs the flow pattern and changes the velocity. So what happens to the mainstream velocity? U becomes, that is the y component of the velocity, mainstream velocity varies, and it becomes u infinity. It was originally u infinity. Now with this disturbance, it slightly changes. We say mark the change as u prime or u dash. So u dash. Now it could be plus or minus. We are just indicating, or it could be uh, positive or negative. We are just indicating it as plus u dash, so that the sign of u dash will take care of the increment or decrement as the case may be. So as because of the presence of the body, the modified velocity becomes u infinity plus u dash. Okay, now how about the velocity v velocity, the second dimension? We are not considering third dimension anyway, so we are concerned about the second dimension v. That becomes v dash. Why? Because to begin with, the v infinity is 0, so there is nothing to add to it. There is no y component. So any induced velocity in the y direction is the y component. So that is equal to that we are considering as v dash. Okay, so uh, we are just considering the disturbance to the velocity component. So we are going to see whether we can rewrite the governing equations using the perturbations. That is, using the disturbances to the velocity field. Okay. And when we do that, and when we try to solve that or try to examine the behavior of those equations, that approach is called small perturbation approach, or the theoretical formulation of it is called as small perturbation theory, which is value which is valid for, or which is applicable for slender bodies at small angles of attack. Now these two are important: slender bodies and small angles of attack. Why slender bodies? Because if the body is blunt, then the perturbations cannot be assumed to be small. We are going to impose the condition that the perturbations are mathematically small or physically small, whereas that's not the case for blunt bodies. So the applicability will be restricted to slender bodies and also small angles of attack because of the same reason. When there is a significant angle of attack, then the variations will be high, or the perturbations cannot be considered to be or assumed to be small. Okay. So in other words, what we are saying is that v u prime is much smaller than v infinity. That is, the disturbance in the velocity is much smaller, significantly smaller than the absolute velocity. And similarly, in the x direction as well as in the y direction, the prime velocity is going to be, or the v prime is going to be much smaller than the if there is any component in the v direction. That is for the that is uh, again, v infinity we are indicating as the free stream velocity. So the disturbance in the y direction is also much smaller than the free stream component of the velocity. So that's what that is. These are the two underlying assumptions that help us reformulate the governing equations in terms of the velocity perturbation. And this is justified. I'm presenting a graph here, a table here. You can examine that more closely when I share the presentation, when I upload the slides. This is just to tell why we are considering slender bodies and why this assumption is valid for slender bodies. I'll just quickly show this. I have done the calculations for a Mach number range of 1.5 to 20 for slender bodies. I have done for non-slender bodies. I don't remember what angle I took, must be around 30 or above that. And I've just done some calculations based on the shock tables. So what we have here is the non-dimensional. What is more important is the non-dimensionalized pressure, which I have shown here, P bar, or the P2 by P1, the ratio of pressure, a static pressure ratio across the shock. Now you can see that P bar, which is defined as P by gamma m infinity square tau squared in rho in P infinity. I'll come to the tau squared factor later. You can see that this value I mean, when you compare that for say bodies which are not slender and which are bodies which are slender, we can do a comparison of the p bar values and see whether these can substantiate the assumptions that we are going to make in terms of the non-dimensional, or rather the small perturbation theory. I'll explain this part of it. I'll show those, or rather, I'll explain these numbers which I have sort of colored here later as we get into the formulation of this. For now, I just want you to be aware that what we are going to discuss primarily are concerned with slender bodies. Today, I'll stop here and we'll move on to the discussion of the presentations. If you have any doubts, please ask right away. No doubt. So we'll continue with the presentation, since I'm also constrained by my cold, so I'm not able to speak so freely. So that's the reason why I cut short the lecture today. But then we can make use of this time to cover whatever each team has to say about their observations in the assignment. So I request all the one by one from group 1, 2, 3, 4, 5 to share the presentation and just highlight what do you observe for the specified Mach number range for the case that we are that is being given. So you can start. Group 1, please. I will stop sharing. Yeah.
Hello, sir. Just a second. Let me share my screen.
Hello. You can again share it. You can share the screen.
Yeah, one second.
Please give me a second. I'm just trying to get the group list also. Just give me a minute. I'll just look. I hope all of you are present. Roll numbers 4, 5, 8, 21, 22. Akash, Shanivasni, Ashwin, Kishore, and Krishnamurti. Yeah, please carry on. Yeah, who is presenting?
Sir, Akshay was roll number 5.
Did you present last time?
No, sir.
Okay, then carry
on.
Here the screen is not. Have you shared the screen? I'm not able
no, sir. Just a second.
Yeah, I can do it.
Is it visible?
Yeah, carry on. Yeah.
Okay. So we were supposed to find the graphs for varying theta from 10 to 90 degrees. So we varied it at a interval of 10 degrees. So what we've done is for the Newton's method, we have the formula Cp is equal to 2 sine square theta, where theta varies from 10 to 90. And for the modified method, we've calculated Cp max using this formula, and this formula was obtained from J.D. Anderson. So we've taken our gamma to be 1.4. So we've calculated our Cp max, varying our Mach numbers. We were given a Mach number of 5 and 20. So both of that we varied, and we got a Newton's method graph and the modified methods. This is for Mach 5 and this is for Mach 20. And from here we are observing that for higher Mach numbers, the modified method approach matches with the Newton approach. And that is considerably accurate over the straight Newton method.
Okay, the second point, what you have said, can you just, for the prediction of, can you please explain what you're saying there?
So what we have done is we've plotted the pressure distribution graphs, and for the modified method is accurate compared to the Newton's normal method. This one's lower, so.
Now, okay, why do you say it is more accurate? Anybody in the team can. Ashwin, can you please explain? Kishore?
Sir, actually, in this case, we, for Mach 20, you could see for small theta, it was like close to this Newton's method, sir. With that Lee's approach and this Newton's approach are close at actually are very somewhat that difference is minor, sir. But when the theta is actually increasing, you could see there is a considerable variation in CP for modified Newton's approach compared to Newton's approach. So, which means this I mean, like this modified Newton's approach is like is giving a proper assumption because
That's okay. That's okay. Yeah. So it's slightly better than the other. That's fine. Yeah. And one more question. Roll number 22 is online. Krishna Murli.
Yes, sir.
Can you explain what is CP max?
So,
CP max. She used. She have mentioned about CP max in the relation, right? What do you understand by CP max?
so blunt-nosed body. So the point at which the flow collides with the body, or the point normal to the surface of the point at which the stagnation pressure.
Okay, so that is downstream of the detached shock, the bore shock, right?
Yes, sir.
Okay, that's right. Yeah, thank you. Thanks for the first group. Second group can share and tell what they find. Anybody who has not presented last time? Okay.
Yes, sir.
Last name was noted.
Lakshmi Shivakumar, sir.
You sorry.
No. Last time Lakshmi Shivakumar presented.
Okay. So who? Yeah, someone else can present. Yeah, Naresh, Nitin.
Yes, sir. Niveta.
Niveta. Okay. Carry on. Yeah.
Is the screen visible?
Yeah.
Okay. Good afternoon, sir. Good afternoon, everyone. These are my team members. Just like the same group that we were given the same question, but there was a vary in mark number. We were given mark numbers of 6 and 24, and we found the CP max for both these mark numbers using the formula given in the textbook. And these are the values we got for CP using the Newtonian method, and these are the modified Newtonian method for these two given mark numbers. The graphs we plotted against for CP versus theta. For CP using Newtonian method, and this is for the modified Newtonian method for Mark 6. This is the comparison graph, and this is for Mark 24. And as Mark 24 is much substantially higher than Mark 6, the graph here is a lot more closer to the original Newton method curve. And this is one of the observations, that as the Mach number increases, the accuracy of this modified Newtonian method becomes more accurate and gets closer to the original Newtonian method. And these are our observations.
That's okay. Can you just come to previous? Yeah. What is your observation about the dependence of theta on CP for different Mach number range? The influence of see, my question is that the influence of theta on the Mach number variation, or rather the CP variation with Mach number.
For the straight Newtonian method, I think it's 2 sine square theta. And for modified
that's okay. I'm not talking about the relation. I'm talking about the observation, what you conclude from the graph. That is, say, for lower Mach numbers of theta versus higher Mach numbers of theta, lower values of theta versus higher values of theta, how Mach number is influencing CP. Anybody can highlight from the graph. Actually, it's quite obvious. That is, say, would you the Mach number influence, is it prominent at lower Mach numbers or higher Mach numbers between the two models, that is the modified and original models? So for example, theta equals 20. Do you have any difference between the two models?
No, sir, not really.
Not. So higher
Okay,
value.
as the theta increases, there is a lot more variation.
Right. What could be the reason for that?
Not sure, sir.
Huh? Why is that you tend to see a variation in CP when theta increases with magnum? It's okay. I think about that because that's an obvious conclusion that you can draw from the graph, right? So just ponder over that why it is becoming more. I can see that from the relation system. Okay. Thank
Okay,
you.
sir.
And yeah, I guess that's it. Next thing, next group. 3. Rajeshri, Renish, Sanjita, Sanjay. Okay, Sanjay presented last time. I don't remember.
No, sir, I did. So Sanjay will be presenting now.
That's it. Sharing that screen.
Just a second, sir. I think he's having some issues with the audio. Just a second.
I see. Okay. So shall we go to the next stream? Probably you can present later. Shall I go to the next group?
Yes, sir. We'll present after this.
Sorry, I didn't hear. What did you say?
So we'll present after this. The next.
That's okay. So we'll go to the next group. Yeah. So group 4 can present. 4, please. You can share the screen and Sanjeev, Shyamala, Surya, Swaroop, Yuvraj. Sorry, not Yuvraj is next. So any of you can present. Yeah. Who did not present last time can present it. Do 4, please.
Yes, sir. 1 second, sir.
Yeah. So you can share and.
Sir, is the screen visible?
It's visible. Yeah. Share it.
Okay, sir.
Sir, I will be presenting now.
Yeah. Sure.
So this is group 4. We done the same calculation for Mac 9 and Mac 34. Can you go to
Slideshow, please. That will be better.
Yes, sir.
Slideshow, if you can put.
So we used the same formula, the Newton's method and the modified Newton's method. In the first method, we don't have any Mach relation. It is independent of the Mach number. And in second method, we have the Mach relation. So it will vary with the various Mach number. Can you go to the next slide? So if you see the graph here, the straight Newton method, there will be no change in that, but the modified Newton method will vary according to the Mach number. You can see the difference between the two graphs and the observation. Next. Yeah, as I said before, there is significant change in the Mach number increase, and you can also see that modified Newton theory is lesser than the original. That's it, sir.
Good. See, the first conclusion that you observation that you put there. In fact, that's very important. That's what I wanted to highlight in some of these. That is, how can you yourself? You can go back to the slide and then explain that in the light of what we have been discussing now, Mach number independence. So, how does Newton's theory concur with the Mach number independence? If you can just explain that based on it, that will be good. Put that on slideshow mode if possible. Be more clear.
Yes, sir. Yes, sir. 1 second. Sanjeev, can you put that in full screen?
Sorry.
I already did. Wait.
1 second.
It's okay if you are not able to, because this is visible enough, but then yeah, it's better. Yeah, carry on. Yeah. All that I'm asking is just to relate this to what we have been discussing in Mach number independence. That's all.
Sir, in Mach number,
so all that we have been saying all along is that when at hypersonic Mach numbers, the pressure distribution becomes practically independent of Mach number, right?
yes, sir. Yes, sir.
Do you see that in these graphs, these matrices?
Yes, sir. Yes, sir. For Newton method, it is independent.
Yeah.
Yes.
Newton's method so Newton method is in concurrence with the Mach number independence theory. Well, that's obvious because that you have 2 sine squared theta. There is no Mach number in that, right? For CP. So obviously it has to be independent of Mach number.
Yes, sir.
Whereas CP, whereas the modified Mach number, modified Newton's theory is slightly dependent on Mach number, right?
Yes, sir. Yes.
Okay, so can I ask anybody else why it is dependent on Mach number?
Sir, it's because of the CPM relations.
Yes, because of the CP. Because CP is a function of Mach number. Because it depends on the Mach number at which the flow, the shock is formed. So
yes.
it has Mach number in it, and that reflects the influence of Mach. Yeah. Okay, thank you. That's okay. Yeah.
Thank you.
Group 3, if you are ready, you can present. Otherwise, group 5.
Yes, sir. I think we're ready. We'll be sharing.
Your group 3, right? Who is speaking now?
Sir, myself, Renish, I will be presenting, sir.
Renish, sorry, that is
33, sir.
Group 3. Yeah, Renish. Yeah.
So we plotted with based on all the equations.
What was the range?
Plotted the CP versus theta graph. Sir, our Mach number is 8 and 30, sir. So we can clearly see that for modifying Newton's theory for Mach number 8 and Mach number 30, it's almost same. So the curve is very much closer, sir, for both of them. And the basic Newton's theory, it does not depend on Mach number. The CP max goes to 2, so it follows the relation 2 sine square theta.
Okay. So in this also we see as earlier, that is up to Mach 20, theta 2025, both the curves are almost matching with each other. Right?
Yes, sir.
So the CP, the modified theory becomes important when theta is higher, right? That is when you have a less slant, or rather when you have a blunter body, right?
Body, yes, sir.
There the
Yes,
difference.
sir.
Yeah. Now on specification is
Also, when
please
yes,
carry
sir.
on.
Yes, sir. Also, when theta is very much less, both the theories are very much closer, sir. So
Yeah,
there is
that's
no
what.
significance between them.
That's what, because when the this one is different, then you don't have this one between CP max and whatever, that formulation sort of coincides to the same, right?
Yes, sir.
Yeah.
The same.
One question that I have is, you are done or you have?
Sir, I think I had done. Next slide is only those observations.
Yeah. Now, say what gamma did you use?
Sir, 1.4.
1.4. My question is, if you were to use a different gamma, because in hypersonic flow, gamma could vary actually. Would you
Yeah, yes, sir.
do you expect any qualitative difference in the results? Quantitatively, yes, they will change, but qualitatively, the relative comparison, do you expect that to vary?
Sir, I'm not sure, but I think there won't be any variation.
Not likely to be. Yeah. Okay, that's it. Thank you.
Yes.
Then we'll quickly go to the next one also.
Oh, okay.
Okay,
Sir.
thank you. You can
Thank you,
stop
sir.
there. Yeah, okay. So group 5, Yuvraj, Shashank.
Is my screen visible, sir?
Yeah.
So yeah.
Who is sorry.
Shashank, sir, from
Shashank, yeah, very
good. So same like everyone, we were given the similar question, and with the Mach numbers of 10 and 36, and we've used the respective formulas for Newton's and modified Newton's method, and theta was varied from 10 degrees to 90 degrees, and the gamma value which we took was 1.4. And these are the resulting graphs for Mach 10, where blue line is Newton's method and orange is modified Newton's method, and for Mach 36, same. The observation from the both graphs were for lower theta and higher Mach numbers, the value of CP is same in both the methods, and also we infer that modified Newton's method is accurate more than straight Newton's method, because it has the relation between the gamma and Mach number of the flow.
good. Okay. Can you just go to the previous graph, previous slide actually?
This one, sir, or the before one?
No, this is fine. Just give me a second. You can just keep it here. Right. Okay. The only thing that I want to ask you here is, say, CP, we can say that there is an increase in CP as you go by, right? And the two graphs are for Newton. Okay. Can you go to the the first one actually, the first graph actually. These are for two different Mach numbers, right?
No, sir. This is for this graph is for Mach 10.
Mach 10. Okay, I understand. Yeah. So this is CP varies from 0 to something like close to 0 to about 2. And go to the next one. Here also it varies in the same range. My question is this actually. Does this mean that the static pressure would remain the same on the body, whether it is Mach 5 or Mach 10 or 36?
I mean, it depends on what order are we considering, sir, because the change in order when Mach increases is in 10 power minus 3.
No. Question is, you are saying that CP is almost, I mean, the values look to be similar, right, in the range.
Yes, sir. The
For
range is similar.
10 and 36 look to be similar curves actually. Values
Yes.
look to be same. So my question is this actually. For a body, can I say that the static pressure distribution remains the same for Mach 10 and 36?
Yes, sir.
Now, is it so?
But the range.
Static pressure. I'm talking about the absolute value of P.
Oh,
P.
okay.
Anybody else in the team can comment on it? Will static pressure remain the same? Because the graphs show that actually everybody's graph showed the same way. CP values seem to be in the same range for the lower Mach number and higher Mach number. So does it mean that static pressure remains the same independent of Mach number?
I think no. I think it's no.
Then what remains constant? The static pressure varies actually. Anybody else in the whole other groups also? Anybody can comment on this? Can you please clarify this issue? He said that it is actually pressure will not be varying. Pressure will be varying. It doesn't remain constant. Then why do we see that the values are almost independent of Mach number? Anybody from other groups also can comment on it, the whole class. Nobody, please. Think of it. We'll discuss that in the next class. I guess because that's something which I've been talking about in the last 2 sessions, I think, repeatedly. My question is this. All of your graphs almost show that the CP values, whether low Mach number or higher Mach number, they seem to be the same. So a Mach number like 10 and Mach number like 36, will they produce the same pressure distribution on the body? That's what I want you to think, or otherwise, what are we saying here as being the same, or why? Okay. So give some thought to it. We'll discuss that in the next class, and then for today we'll stop here. Okay. So this question is not only to group 5, to the entire class. So anybody can comment on it next. Okay. Thank you. We'll stop here. Bye.
Thank you, sir.
Thank you, sir.